After studying this module, you shall be able to know the origin of the terms erythro and threo isomers, learn about the projections of these isomers, understand the relation between enantiomers and diastereomers and erythro and threo isomers, analyze some examples of these isomers. In the previous modules, we have discussed that the simplest source of dissymmetry in an organic molecule is a carbon atom, to which 4 other atoms or groups, each of different kind from one another, are attached. The regular tetrahedron provides an achiral 3-dimensional framework of TD symmetry having 4 topologically equivalent vertices. However, in an aforementioned case, all elements of symmetry disappear and the tetrahedron turns into a 4-point chiral simplex of C1 symmetry, which is non-superimposable on its mirror image. A unique feature of this chiral tetrahedral model is that transposition, exchange or permutation of any ligands reverses the chirality of the center, giving a new stereoisomer. If all the ligands are achiral, the transposition leads to an enantiomer, while one or more ligands are chiral, then a diastereomer results. Nomenclature of molecules containing multiple chiral centers. An introduction to erythro and threo nomenclature. Numerous natural products such as steroids, terpenes, carbohydrates, proteins and alkaloids contain 2 or more chiral centers. It thus becomes mandatory for any organic chemist to have an in-depth understanding of a stereochemistry of the molecules with multiple chiral centers. In this context, some noteworthy points are: addition or creation of a new chiral center to a molecule already containing one or more always gives rise to a new diastereomer, the number of which doubles for each addition except in cases of degeneracy. In molecules with multiple chiral centers, diastereomers and enantiomers occur side by side. Depending upon the symmetry, any diastereomer can be either chiral or achiral, or so to say resolvable. Special systems of nomenclature are needed to designate 2 diastereomers which differ in relative configuration. The relative configuration at adjacent chirality centers in a variety of natural products may be described by erythro and threo nomenclature. In this form of nomenclature, if identical or similar substituents are on the same side of the vertical chain in a Fisher projection, the erythro isomer results. If these substituents are on the opposite sides, the threo isomer results in the Fisher projection. Today, the erythro-threo nomenclature is still used only in the carbohydrate chemistry. The number of stereoisomers, enantiomers and diastereomers goes on increasing with the number of chiral centers. It is also noteworthy that n chiral centers give rise to 2 to the power of n stereoisomers in general except for few cases. Thus, an aldotetrose C4H8O4 has 2 stereo centers and therefore can exist in 4 stereoisomeric forms as 2 pair of enantiomers called as erythros and threos. Molecules that contain 2 asymmetric atoms in particular have been used extensively in mechanistic studies, and a special nomenclature and special forms of notation for such systems has sprung up. In a molecule with 2 stereo centers, when there are 2 groups which are common to each carbon while the third is different, that is CABX linked to CABY, gives rise to erythro and threo diastereomers. Since erythros and threos, as discussed earlier, are diastereomers, Their diastereoisomeric pairs of molecules which have two adjacent stereo centers are designated erythro and threo, depending on whether similar groups are on the same side, which is erythro, or on the opposite sides, which is threo, on the Fischer projection respectively. As shown here in the figure, the erythros minus, erythros plus, threos minus and threos plus forms are shown. Here the plus and minus notations are specifically for the direction of rotation and do not carry any weightage to the configuration. Fischer, Newman and Sawhorst notation of erythro and threo forms. As for notation, it might appear at first sight that Fischer projection formulas as shown in figure should be adequate for the representation of a compounds with two asymmetric carbon atoms. On drawing from the Fischer projection directly, the Sawhorst projections, the eclipsed form has more crowding or steric hindrance. However, the staggered form is more desirable as representation shown in the molecule. Let us observe the Sawhorst and the Newman formulas of 3-bromo-2-butanol from Fischer projection. It can be seen how the eclipsing is leading to the more of steric hindrance, while the staggered conformation does not show that kind of a steric hindrance and henceforth less of the inter-electronic repulsions in a molecule. The Fischer projection formulas at a glance whether one is dealing with erythro or threo form, but the Sawhorst and Newman formulas do not and usually require at least a mental process of rotation around C2-C3 bond until one can decide which is which as depicted in the figure. Yet another way of showing compounds with two asymmetric centers is by the means of flying wedge formulas as shown in the next figure. The flying wedge formula for the threo and erythro forms of 3-bromo-2-butanols is very well depicted here in the figure. Properties of erythro and threo isomers. Two erythro isomers constitute a pair of enantiomers, which are also called as the optical antipodes, which when mixed gives a racemate. The threo isomers are also a pair of enantiomers which also form a racemate on mixing. The properties of threo racemate are different from those of the erythro racemate. Thus, there are only 4 optically active isomers of chloromalic acid and 2 racemates. Erythro and threo is a shorthand method employed by the organic chemist to name appropriate compounds. However, if one has to refer to a particular enantiomer of the erythro and threo pair, R and S notation is used. The threo and the erythro isomers of chloromalic acid are here shown in figure. The properties of the threo racemate are different from those of the erythro racemate. Thus, there are 4 optically active isomers of chloromalic acid and 2 racemates as shown here in the table. The melting point observed is similar for the erythro minus and the erythro plus form. However, this differs with the other isomer of the threo form. The optical rotations are also found to be different for the 2 isomeric structures. The melting point of the erythro racemate and the threo racemate are also different, as shown also with the constants of diethyl ethers of erythro and threo racemates, which are found to be different. The erythro and threo systems of nomenclature works very well for the compounds for the general formula R, CAB, CAB R dash, that is only one of the substituent attached to the carbon-carbon bonds is different, and even CABX and linked to CABY as stated earlier, in which at least one pair of the substituent matches. On the contrary, This system falters badly for the compounds of the type RCAB, CCCD, R' which has no two substituents properly matched. One has to decide the similarity of groups on the basis of the steric bulk, state of oxidation or electronegativity, and the system becomes ambiguous. Some more examples of erythro and Threo nomenclature: 2,3-dichloropentane. The Fischer formula is shown, which is depicting two eclipsing pairs of chloro-chloro and hydrogen-hydrogen attached to the two adjacent carbon atoms. The Sawhort's formula for the erythro and the Threo forms are very well shown here in the figures, which are also indicative of the steric hindrances influenced by these molecules. 2,3,4-trihydroxybutanol. The two forms are shown here by the Fischer formula as well as the Sawhort's formulas. In this module, to summarize, we have taught you that it is mandatory for the organic chemist to have an in-depth understanding of the stereochemistry of molecules with multiple chiral centers, as numerous natural products such as steroids, terpenes, carbohydrates, proteins and alkaloids contain two or more chiral centers. The number of stereoisomers, enantiomers and diastereomers, both of them, goes on increasing with the number of chiral centers. It is noteworthy that n chiral centers give rise to 2 to the power of n stereoisomers in general, except for few cases. An aldotetrose C4H8O4 has 2 stereo centers and can exist in 4 stereoisomeric forms as 2 pair of enantiomers called erythros and threos. In a molecule with 2 stereo centers, when there are 2 groups which are common to each carbon while the third is different, it gives rise to erythro and threo diastereomers. Till today, this nomenclature is used in carbohydrate chemistry. 2 erythroisomers constitute a pair of enantiomers called as optical antipodes, which when mixed gives a racemate. The threoisomers are also a pair of enantiomers which also form a racemate on mixing. The differing properties of each isomer are also discussed. Various notations for writing the two forms are described along with the emphasis on the stability of each form. It is noteworthy to point out that this system falters badly for the compounds of the type RAB, CCC, CD, R' which has no two substituents properly matched and all the substituents are different.